Welcome everybody to this month's edition of the first Friday webinar in the Euro Practitioners Forum. It's a pleasure to have you here on this day. Today we're going to be hearing about Hexaly, a new kind of global optimization solver. Although in his bio, Fred says he's founded Hexaly in 2012. So I suppose the definition of new depends. He will explain, I'm sure.
Exactly.
But before we do that, I wanted to give a little bit of introduction about who we are in the Euro Practitioners Forum and what we are trying to achieve. So, the Euro Practitioners Forum, or the working group on the practice of OR, is happening under the organization of Euro, and our charter is to be a natural home for practitioners, mainly outside academia, although of course these distinctions vary a little bit in our careers and so on. We want it to be a forum where we can network, build and support one another, where we can share experiences and solutions to the everyday challenges and opportunities we face as OR practitioners. And we would like to learn from one another to improve ourselves and just to keep up with the field. I think it is true that in a lot of organizations, the OR department can be a little bit lonely, and so it is also a very good opportunity to connect with your fellow operations researchers here. So hopefully this also gives us the opportunity to meet and inspire and be inspired by like-minded people from across Europe. So to that end, the Euro Practitioners Forum organizes occasionally physical events. The next one is the Practitioner Forum Conference in Warsaw, Poland. It's going to be in April 2026, as you can see. We are also doing these virtual events. We have had a variety for some time. Right now, what is planned in the next few months is only the first Friday webinars. Follow our LinkedIn page, which we have been launching for a little while. And here we try to post the things that are coming up and keep you updated. So generally, I think if you follow the LinkedIn page and are a LinkedIn user, at least a sufficiently active LinkedIn user, as well as following the Eventbrite organization, you will find out what is generally happening. And if any of you listening here today feel like actually you think you could give a good talk at one of these webinars, please feel free to reach out to us. We are always happy to find new people who can talk. This meeting is being recorded, which means that if you, at the end of the talk, would like to raise a question and don't mind being in the video, you can raise your hand and we might unmute you and let you turn on the video for it. Other than that, you're also free to ask questions in the chat and I will read them out to Fred at the end. We might also stop sometime during the talk to take questions. Let's welcome our speaker, Fred Gardi. He is an operations research expert with more than 25 years of experience. And he has been working in Hexaly for more than 10 years now. And today he's going to talk to us a little bit about what that is. Welcome, Fred.
Thank you for the invitation, for the introduction. So I'm Fred Gardi, one of the founders of Hexaly. I'm the CEO of the company. I'm based in Brooklyn, New York. Today I will give an overview of what Hexaly is. I will not enter too much into the detail, especially of what is inside. I will give you an overview of what is inside, but not detailing too much each technicality we have. So the goal of the talk is to explain what is Hexaly in comparison to traditional MILP solvers, where it brings the largest differentiation. So where it is really good in comparison to traditional solvers. So Hexaly, it's not really new. You mentioned that, yeah, we mention it as a new optimization solver. It's not really new. We started in 2012. We bootstrapped, so it was very slow at the beginning. The first 5 years were really slow in R&D because we were just 4 people, slow in selling, customer acquisition. But the last couple of years, we had very good traction because also the solver now is more mature, very robust, and is recognized to be really, really strong, not to say the best on a couple of problems in supply chain and workforce management, especially. So routing, scheduling, packing, and I will explain today why is so fast on these problems. So it's not really new. It's not really new, but we were not very well known until then. We didn't publicize it so much, especially in academia. We were cautious. We didn't want to show things that are not really good, I would say. Now, for a few years, I would say more than 5 years now, it's really good. And yeah, as I explained, we have some traction. We have doubled the number of clients the last 3 years. We have 400 clients company now. Big companies, but also a lot of small and medium software service businesses. We have two offices, one in Brooklyn, New York, where I'm based, and one in Paris, France. So we focus on a solver. We develop a solver, the optimizer, but we also have a studio, a platform around it. I will explain. I will give a few words about that. If you have some questions, maybe we discuss that with Torko. If you have some questions, some important question during the talk, you can interrupt me. You can ask question. In any case, we'll have 10 minutes at the end of the talk, 10, 15 minutes to answer questions. So here are some companies that have switched to Hexaly. I would say that people don't switch to Hexaly, don't replace Gurobi, Cplex, or their favorite solver by Hexaly. Some do that now. They rarely switch and abandon the previous technology, so MILP. But most of the companies adopt Hexaly first because we have a price which allow to do that, which allow to have Cplex, Gurobi, Express, or any of the solvers, and at the same time to have Hexaly because we have very, very simple and competitive price in comparison with Gurobi and Cplex especially. And so I will not detail that today, but we have a price for enterprise. We have a price also for startups, small and medium businesses. If you're interested to know more about our pricing, which is really simple and very competitive, with an unlimited license, you can contact me, fgardi@hexaly.com. Very easy to find me. You can send me an email. We can have a short talk about that. So you can see that, yeah, we have big companies that have adopted Hexaly, Amazon, FedEx, Procter & Gamble, Starbucks, Sony, Airbus, Bosch, Toyota, a number of very big companies. But again, we have approximately 200 software, service, and small and medium businesses that rely on Hexaly, that power their products, especially for supply chain management. They power their products using Hexaly today. So, as I explained, the main product is Hexaly Optimizer. This is the main product we have, and this is where we focus a lot of the effort, a lot of R&D. So the team is now 50. We have 50 people, 45 in R&D. This is where we invest the most, the optimizer. We want to become the best in the domain, so offering the best optimization solver. So we compete seriously with Gurobi now. And we expect to become the best in the next 3 years, increasing the size of the team to 100. This is a big difference with Gurobi. As you know, Gurobi has a very strong technical team, a very strong R&D team, but they have just 10 people. At Hexaly, we invest much more, and we want to grow the team to 100 people in R&D. It's something to organize the development, but we know how to do that. We do it very well. So I will focus on the optimizer today, but we also have Hexaly Modeler, a modeling language. It competes with GAMS, MPOL, AIMS, or other modeling language, and it's integrated inside Hexaly Studio. Hexaly Studio is a platform, web-based, local-oriented to build applications. So from prototyping to deployment. So you prototype, you develop, you deploy on the studio, and you can do that very quickly. Our goal is to offer an environment which streamlines the development cycle of people interested in building optimization applications using Hexaly. This is a companion product. We launched it 3 years ago now, and it has been adapted by companies like Renault or Airbus, Veolia in France especially. They use it now to build applications. And at last, we have Hexaly Cloud. This is really optimization as a service. It's not the same cloud offering that Gurobi or Cplex. Here, it's really optimization as a service. It means that you can install Hexaly as usual on your laptop or in an application on a server. Then you change the license file, and the Hexaly executes in the cloud transparently. When you run it, Hexaly build an instance, encrypted, fully secure, send in the cloud, it's solved in the cloud, the solution come back encrypted, no data are stored in the cloud. It's like consuming the cloud. And it's really back and forth, almost no overhead because we have servers everywhere backed by AWS, Azure, GCP. And it's really optimization as a service, and it's part of the license price. Unlimited use. So very simple. The compute is on us in this case. Again, I will not detail that too much today. I will explain what is the difference between Hexaly and traditional MILP, because Hexaly is a kind of a new MILP solver. So what are the differences with MILP? First, in terms of modeling, and then we will see the solving. So at the first glance, when you look at Hexaly Optimizer, it's really like Gurobi or Cplex or any other solver. You have an API, a modeling interface. It is accessible from Python, Java, C#, C++, or as I mentioned previously, from Hexaly Modeler. And this is the same modeling power you have with all the APIs. You can express the same, no difference, just the language. The syntax is different. So you build a model, you run the optimizer, you get solutions, you get bounds. So it's really, and you can get optimality proof, inconsistency proof. So it's really like MILP solvers, any solver. In the backend, we have a number of methods, hybridized, and yeah, it delivers solutions, bound, global bounds. It's really a global optimization solver. And apparently this is the same, but when you use Cplex or Gurobi. But there are things that are a bit different in the modeling and in the solving, so in the backend. I will detail that. But again, you use it very similarly to Gurobi, to Cplex, and other solvers. Give the model, launch it. You can stop the resolution. You can reopen the model. You can change some expressions, constraints, objective. You can relaunch. You can do a lot of things. We have callbacks. We have everything like MILP solvers. What is different? What is different is that when we started more than 10 years ago, we wanted to build a new kind of solver, something better. First, in terms of modeling, not just to offer a better modeling, easier modeling to users, but because modeling is also a way to capture structures, mathematical structures that you can leverage using algorithms. Having structures in the backend is critical to make algorithms faster, more scalable, and to leverage more techniques from the state of the art. So we wanted something higher level. And so Hexaly modeling language I mean modeling language, the mathematical language, which is accessible through Python, for example, Python API. I will call that a language. It's an extension of all what you know today. And it's an hybridization of all what you know today. So it extends MILP, mixed integral linear programming. It extends nonlinear programming, mixed integral nonlinear programming, MINLP. It extends CP, constraint programming, and black box optimization, BBO. So Hexaly hybridizes all these formalisms and unify all of that. It offers a unified API that supports all these concepts. Here you have in the different languages. So Hexaly API is very expressive, very broad modeling language, modeling power. You can possibly model any problem using Hexaly because we also support black box optimization, which means that you can implement your own functions. You can use a piece of code as a function that you can plug to your Hexaly model, and Hexaly will call it appropriately. We also have surrogate modeling. I will not detail that here, but you can make simulation optimization. You can make machine learning plus optimization. This is something you can do very easily. So plugging, for example, a machine learning code to express a constraint, which is stochastic, this kind of thing. You can do that. Very expressive and flexible modeling API. What is really new? Because we have taken some concepts, some existing concepts in the different technologies, in the different domains. Now we have introduced some really new concepts. And these new concepts are related to set algebra, permutation algebra, and interval algebra. And more than that, function algebra. This is something really new. It's inspired from constraint programming, from some old papers in the 80s, but it was not implemented in modern constraint programming solvers. And so we have it. So I will detail a bit what it is, and I will give an example of what is a set variable, what is a list variable. It's list is a term we use for permutation inside Hexaly. What are the intervals and what are these functions I mentioned here? But here you have the concepts that are really unique to Hexaly, and that explains why it's not compatible with existing technology or existing modeling languages like MPOL, GAMS, or the APIs like Perl, Pyomo. They don't implement these concepts. So you don't have these concepts available through this API, and you cannot use Hexaly at best and its flexibility. So that's why here, this is the main drawback. This is the main drawback with Hexaly, is that having some additional concepts, you have, in some cases, not all the time, but in a number of cases, for a number of problems, you have to translate, you have to reformulate your model. So Hexaly models would not be exactly like CPLEX or Gurobi models, MILP models, or CP models if you use CPSAT in OR-Tools. So this is the main drawback. It's not plug and play if you want to get the best performance from Hexaly. So here, an overview of all the mathematical functions you have in the Hexaly API, whatever the language you use, so Python, Java, C#, C++, or the modeler. So you can see that you have here's the traditional decision variables, so Boolean variables, floating points, so read variables, quantitative decisions, integer decisions. But we have also these concepts that we have introduced, so set, list, interval variables. You have the ability to build quadratic expressions very naturally using the product, but more than that, polynomial expressions. So we support polynomial optimization. exponentials, trigonometric functions, all logical operators are available, like the if then else. So no big M in Hexaly, you can use the if then else operator. If this expression is true, I want to use this expression in my constraint. Otherwise, I want to use another expression. Very expressive, very generic. I mentioned that we have these new concepts, so set, list, interval, and all related algebraic operators that can operate on them here on the right. There are more than that. I have not give all the operator. It's really set algebra. So you mentioned you manipulate sets and you can make union, intersection, a number of things like that on these concepts. Black box functions, you can define your own function as a piece of code that you can put everywhere in the model, in constraints, in the objectives. And at last, we support multi-objective optimization. So you can give a number of objectives in order. We will optimize them all and in order, and you will have some solutions and bounds. You will have bounds, lower bounds or upper bounds, depending on the if you minimize or maximize, but we will have bounds for each objective. So very convenient in industrial optimization. As you know, you generally have several objectives to optimize. Here wants to give you a small example in nonlinear optimization, just to give you an idea of the power, the expressiveness of Hexaly. And also to explain that Hexaly is not just good for discrete optimization problems. So we have some clients that use it for solving linear problems. Okay, it works. Nonlinear problems, quantitative nonlinear problems, it works. Our point here is that I really publicize it for discrete optimization. So like routing, scheduling, packing, clustering, matching, assignment, location, network design problems, all these problems you have in supply chain and workforce management. I publicize it, we publicize it a lot because on these problems, it makes a huge difference. Now on pure linear, convex, or nonlinear problems, it depends. It depends the nature of the problem. You have to test. But to give you an example here, very small and toy example, I want to optimize the design of a bucket. I'm an industrial. I have some, and my company transform some pieces of metal, some disc of metal into a bucket. I build buckets. At start, I have some disk. I have a disk. I consider to have some disk of radius 1. So the surface is pi. And I want to transform this surface into volume. And I want to build a bucket, and I want to maximize the volume of the bucket. So here you can see here the geometry of the bucket. Here we have 3 parameters, 3 variables to decide. So small radius, the large radius, and the 8. So again, very small problems, just 3 variables to decide. I give you here the equations taken from a book that express the surface and the volume depending on the small radius, the large radius, and the 8. So you can consider that it's given. We have these equations to derive to compute the surface and the volume. How we write an optimization model to solve this problem. In Hexaly, we can really write the problem as it is defined in terms of business or engineering, I would say. So first so here it's written using Hexaly modeler, but the model will be very similar in Python or any other language. So first you declare the 3 variables to decide. So the small radius, the large radius, the 8. Here, these variables are quantitative. They are real variables. We use float variables to model that. So here it's normalized between 0 and 1, but it's not a Boolean variable here. It's normalized between 0 and 1 because I know that the disk has a radius 1, so all dimension will be lower than 1, but you can put 0, 100, 0, 1 million, no worry, it works. It's a continuous variable. Second, we define the surface and the volume. So you can see here that the surface and the volume can be written really as an equation of the book. It's really a direct translation. So you have the power, the function power you can use. You have the square root. You can multiply variables together. This is what we do here. So you compute here. You write the expression. So how do you compute the surface? And you say, okay, the surface must be lower than pi. This is the surface of the disk. And now the same for the volume. I compute the volume and I maximize the volume. I launch Hexaly. Here it's an easy problem for Hexaly. You can here you have optimal solution found in less than a second. You see here optimal solution, the objective function, the value of the objective function. So this is the volume of the bucket. Here 0.68, 70, 95. It's a volume found. And you have the bound here. This is an upper bound here. This is an upper bound on the volume. The bound, the optimality gap is lower than 0.01%. We stop the search. This is something you can parameterize if you want to have a finer precision. But okay, we have this solution, and you say, okay, it's easy. In fact, this problem is not so easy to solve. For example, Cplex doesn't solve it. If you want to express it like this, you cannot solve it with Cplex. It will tell you that the matrix is not semi-definite positive, something like that. Because here the surface is a quadratic expression. We have a polynomial of degree 2 here. We have a power of 2. You can prove that this expression is convex. But the volume here, it's cubic. This is a polynomial of degree 3. It's a volume. And it's non-convex. And so it's a non-convex, non-linear problem you solve in a continuous space. It's not so simple. And for example, Cplex doesn't solve this problem. If you want to express it, you have to approximate, to change its definition. And Gurobi, more than 2 years ago, the same. Now they solve it because they are going to MILP. Now they extend the capability of Gurobi, especially with the last version 12. But a few years ago, nobody was solving this problem. With Hexaly, we solve it very quickly, and you see the expression of the problem is very simple. It's a direct translation. This is really what we wanted from the beginning. When we started in 2012, we wanted to build a very expressive, very general solver that can solve these problems at hand. And this is what we have. I don't claim that we can solve any nonlinear, non-convex problem in seconds. Not here, it's a small problem, so it's fast. Now, as you know, these problems are difficult to solve, like discrete problems, and so it's not fully scalable. But you can expect very good solution very quickly, even if it's not optimal solution. So what makes Hexaly unique? What makes Hexaly unique? It's really the concepts I introduced previously related to set and list. These concepts are the idea to introduce set algebra into a mathematical optimization API, set algebra and permutation algebra, interval algebra as well. It's really new. And for discrete optimization, it's really a game changer. It's really an innovation. It's really a game changer, both in terms of modeling, easiness, compactness of the modeling, and in the capability it brings you to solve these problems in the backend. So what is a set? A set defined over a parameter n is any subset over 0 and -1. X here will be determined by the solver. So the values in the set will be determined by the solver, and it can be any subset over 0 and -1. So if n equal 10, it can be 0, it can be 1, it can be 1, 0, 1, 2, 10, 9, 8, and 9. It can be empty as well. It can be empty, as a set can be empty, X can be empty. The solver will define what values are in the set, knowing that each value is unique over the domain. There is a uniqueness of the values, what we call the items here, and the size is variable. This is a key thing. The size of the set is variable. It's particularly used for modeling, packing, and clustering problems. Now the list. List variables are just the extension of sets, taking into account the ordering, the order of the values and the items inside the set. So here, Y is any permutation over any subset over 0 and -1. So it can be empty, it can be 0, it can be 1, it can be 1, 0, or 0, 1. It's two different lists for Hexaly. Again, uniqueness of the items inside the list, variable size, and here's items order. So this is a definition of what is a set variable, what is a list variable. And having these concepts, you're good to model in a much better way, much more compact, much more natural way, problems like routing, scheduling, packing, etc. But it's not enough. What you need as well is you need to be able to operate on these collections. Sets and lists are collection of numbers, and you need to operate that are generally considered as indices. It's kind of, you have objects with some indices, and you want to operate on them using functions. And so we have a very abstract definition of functions inside Hexaly. You can apply functions on sets. Any functions like the sum, the product, the min, the max, the end, the or, but also set operators like intersection, union. You can apply these functions to collections like set, list. And all these collections are iterable. You can iterate on them, and you can apply functions. So to be more concrete here, for example, imagine we want to compute the sum of squares of a set of integers defined over 0, x minus 1. We have a collection, 0, x minus 1. X being an expression, x being a variable of the problem. This is a big difference with MILP, even with CP. Here, x can be a variable of your model. And so it will be defined, it will be determined by the solver. You don't know the value of x when you start the execution. And you want, at some point in your model, you want to compute the sum of squares over this collection. You can, so what you want to do is you want to write this kind of expression. Here, I want to compute the sigma. Here's the sum of I to the power of 2 from I equal to 0 to x minus 1. And x, this is a big thing again. Think that x is a variable of your model. Here, to make things simpler, I consider x is a decision variable. It's not an expression built over decisions or over expressions. It's directly an integer variable between 0 and 10. I want to compute the sum of square. Here, I can write this expression in Hexaly. You can write it in Hexaly modeler. Here it's using the Hexaly modeler syntax, but you can write it in Python. It's very similar in Python, in Java, in C#. The difference is that it's just more variables in Java, because everything is more variables in Java, for example. But here the sum of square is just the sum from 0 to x minus 1. This is, here's the syntax to exclude the last item, so x. I compute I to the power of 2. This is what we call a lambda expression. So we use here some concepts from software engineering, computer language, computer programming, programming languages. Modern languages expose lambda function. You have it in Java and C#. We have introduced lambda function, the concepts of lambda function, into a mathematical formalism of the formalism of Hexaly. And this is really new. This is something which is really new. So you can define this kind of so a function can be expressed like this. So you can make, for example, function can be here the sum, the product, the mean, the max. So you can make the mean over a collection, whatever the collection you have, a set, a list, or an array. And you can apply a lambda function you declare on the fly here. So here this is I to the power of 2, but you can imagine an expression which is nonlinear, which is whatever. So again, very new, very, very expressive, and very nonlinear. Here you can have several levels of indirection in what you do here. So a concrete example. This language was defined to solve real life problems, and you can express in a much easier way, much more compactly, some real life, very complex, dirty problems. But I will give you an example on a very simple problems in its definition, the traveling salesman problem. It's very good to start with because it's very simple definition. Everybody knows the TSP. So you have a number of cities to visit. Each city must be visited once, and you want to minimize the total travel distance. You have a distance, a metric expressed on your graph, and whatever it is, you can imagine that you have a distance matrix that gives you the distance for every pair of point, and you want to minimize the total travel distance. This is a good problem because expressing this problem, TSP, which is so simple in its definition, expressing it using the mainstream optimization solver, which are MILP solvers, mixed integral linear programming, it's not so simple. It's not so direct. For example, this is what we learn at school. So TSP is a good example where we can build a model with an exponential number of constraints. So this is the seminal Danzig, Ferguson, and Johnson formulation back to 54, but it's still what is used a lot in practice here. This is the formulation where you have an edge for a variable 0, 1 for each edge. So you will select the edge in the tour, and you express the constraints, so the subtour elimination constraints. And you have an exponential number of these constraints. So you can generate all of them, but it's not scalable. So if you don't want to generate all of them, you can make a branch and cut approach. You generate them on the fly. This is the root of the branch and cut approach that you learn at school. Okay, it's very nice, but it's also very sophisticated, and you have to build everything on your own. Here, you have a solver like Concord, the famous Concord TSP solver, which is dedicated to TSP problems, that implements these techniques. But now, if you want to build it on your own, so no MILP solver implement that. You have to implement it on your own. But this is the most common formulation because this is the one that brings the best linear relaxation. So you have the best linear relaxation, and so it cuts, and you can derive solutions, especially for small to medium instances. You can solve problems using it. Now it's not really scalable. You have to work much more if you want to make it scalable. You have different formulations. This is the most common formulation. You have plenty of formulations, especially based on commodity flow approach. Here I give you one for Gavish and Graves. Here it's so here it's different. You have a quadratic number of variables and you have a quadratic number of constraints. So it's polynomial formulation, but the relaxation is not good. You have books, answer books that give you some formulations for the TSP. Here you have a book which is a survey of all integral programming formulation for the TSP. But again, the definition of the problem essentially is so simple. You want to find a permutation of the cities that minimize this function. So the sum of the distance between the first city I select to the second, etc., and the loopback. The definition is a few lines, and you have no MILP formulation and no CP formulation, no whatever that is close to this definition from the book. And introducing the concepts I mentioned with set and list and the related algebraic operators and the function, this is something you can do with Hexaly. Now you can express this problem in a much easier and compact way with Hexaly. Here, thanks to the list variables. As I explained, list, the kind of permutation, or can be any permutation over any subset between 0 and -1. So here, naturally, I can use a list to model my tour. So here I declare this variable, cities, which contain, that will contain the cities in order, so the numbers corresponding to the cities. I have n cities, so I declare the list over n. Remember that list can be empty. Basically, there is no constraint over the list. So I need to constrain my list to contain all the cities. A way to do that is that I use the operator count. I count the number of cities. I want this number to be equal to n. This is a constraint here. This is a constraint. I force the permutation to be full, to contain all the cities. And now I can write my distance. My total distance can be written. So it's what I want to write is the equation from the book here, the expression from the book. So I want to sum the distance between each pair of consecutive cities, starting from the first city to the last one, and to have to add the loop back. Again, distance can be any function. Here it can be a distance matrix. I took a distance matrix here, but it can be any function. It can be even an external function that you define by a piece of code. So you can see here, I sum the distances from the first city to the last one. So I will take the distance between the city in position I-1 to the next one in the list. I sum all of that, and then I add the last segment from the last city to the first one to have the loop. And you can see here that I launch it. I launch Hexaly on an instance with from the TSP-lib, the famous TSP benchmark, with 443 cities. So it's not really big, but it's not so small. And here you get optimal solution in seconds. In a few seconds on a basic laptop, on my laptop, I have a basic laptop, you can get the optimal solution. You close the gap here. So it's not just, okay, you find the solution, you find it, and you prove this is the best here, really. You have the objective value here, you have the bound, the gap is 0, it's optimal. So here you will tell me, okay, you introduce some concepts. Why this difference also in solving? Why? So we see the difference here in modeling. It's easier, more compact. You have a pretty elegant model to model these highly discrete optimization problems, but how it makes a difference in terms of solving. So in terms of solving, we have a combination of many exact and heuristic methods. It's also what is possible having this very broad modeling API. We have very high level models, and we can, in the backend, implement a lot of techniques. So we have the techniques you have in MILP solvers, CP solvers, MINLP solvers, so spatial branch and bound, constraint propagation. We have all these technicalities. It took 10 years to implement all of that. Everything is proprietary here. But what makes a huge difference, and especially on these models that are built over set, list, and intervals, this is what is involved here. So we have two classes of techniques from the state of the art that nobody else have as we have implemented them. So first, it's local search. Local search, neighborhood search methods, really as it's implemented in the state of the art. Not a local search in the branch and bound tree. Here it's really local search as it's implemented in the state of the art because we have structure like set list where we can rely on to make these techniques possible and fast. This is a big thing because local search, as you know, heuristics are critical to get speed and scalability. But the last couple of years, we have started to implement something which is also really critical in the state of the art for all these problems I mentioned. This is column generation. Column generation, branch cut price techniques, also decision diagrams and column elimination techniques, very new techniques, I would say, at the forefront of the research. If you want to be the state of the art on routing, on scheduling, on packing, on clustering, all these problems, you need to have these techniques from the state of the art. And this is what we have. And this is possible because we have these higher level models. I will conclude showing you a benchmark to explain the difference in things of speed and scalability. A benchmark on the TSP I just showed previously. Here I compare Hexaly, Gurobi, and Concord. Concord is the state-of-the-art solver for TSP. This is the best code you have to solve TSP problems. It's better than Hexaly, faster than Hexaly. It implements the state-of-the-art branch and cut, but also, which is critical, a state-of-the-art local search derived from Lynn Kernighan and the implementation by LSGO, so LKH. It's combined together inside Concord and it delivers the state-of-the-art. So here you can see that you have the size of the instance in the bottom, in the axis here, the size of the instance to solve. Here's the gap to the best solution found so far. So the best is Concord. So 0% means that it's the solutions delivered by Concord. And so we compare here Hexaly and Gurobi. So Gurobi here is used, we use the code given by Gurobi on their website, so the TSP code. So it's a code based on branch and cut with the implementation of lazy constraints. It's a good code, but there is no local search. In Concord, you have branch and cut, a state-of-the-art branch and cut approach with a lot of cuts from the research, and also local search. And precisely here, you can see that local search is critical because Gurobi doesn't scale at all with this model. Here, this is I would say, a basic branch and cut approach based on Gurobi, which is considered the best MILP solver today. You can see that very quickly with instances with 300-400 of cities, you have no solution. Here's the crosses for no solution. You see that you have optimal solution found here when it's lower than 200, but very quickly you have no solution. With Hexaly, you have solutions, you have bounds, you have optimality proof as well. Here, when it's small, you have optimal solution found. You have a number of optimal solution found here, but it's scale. It's scale like Concord. So it's scale like Concord because we have these technicalities that are embedded inside Concord. We have them inside Hexaly. So there is no magic, there is no quantum things or GPU things or new algorithms, magic algorithms. We have the state-of-the-art running on a laptop, just 4 cores enough. It's okay. You can scale to 10, even 100 cities and get very good solution in just 1 minute of running time. Here, the benchmarking on 1 minute of running time. And so the difference between Hexaly and Concord is that Hexaly is really generic. It's not just designed to solve TSP. So if you add constraints, you change your objective, or if you want to solve capacitated vehicle routing problem, for example, it's a natural extension of TSP as you have in industry. You can model that, extending the model using the operators, and it's okay. You get a very good solution very quickly. I would stop here to get questions.
The first thing I did as an operations researcher was a GPU accelerated implementation of the LKH heuristic. So it was a treat to see your comparison here. And I think of the graph you showed, I mean, one thing is beating a pure branch and cut approach on the TSP, which I mean is not really the right approach to take. but you're following Concord pretty nicely with the
Concord
generic
is the
software,
best.
which
Yeah,
is
Concord
exactly.
is really the best branch and cut you can find with the best local search you can find for TSP. This is LKH. Here it's not on GPU. Here it's on CPU. We compare in CPU here. And yeah, this is the point.
Yeah.
What we want to show is that, okay, we don't compare with a basic branch and cut. We compare to show the difference with Gurobi if you use it basically, but we compare with Concord here. And this is
But
where
I
is
was
the
curious.
difference.
You said, I mean, you mentioned decision diagrams. For those who are
Yeah.
listening, we had a good webinar on this in February by Jan Willem van Hove.
I know
So
very well, yeah, William,
Yeah.
yeah. We
So,
inspire a lot from the research. Yeah, they did.
You
Yeah,
can check out the webinar recording online to all of you listening.
Sure.
But I was curious, did you, when you started this, you said you found some old papers from the 80s. Was it your opinion that, let's say, main solvers of the time did not use the proper methods? You say you are this set-based modeling. Do you think this is something you developed in-house, or is it something that you found in the literature that you think they overlooked?
So we have developed in-house. So you can find some old papers in the 80s that introduced set variables in CP, but so list variables, so what we call permutation, were introduced in a number of solvers, so prototype solvers. You have the ability to implement to model a permutation, but it's not enough. What was in the literature was not enough to model problems like, for example, this one, to model the capacitated Baker routing problem. If you just have a permutation, it's not enough. You need to have more operator. You need to have the ability to implement lambda functions. And so lambda, for example, it's really new. It's not new because you have that in computer programming. You have in programming languages, you have lambda functions. We have taken these concepts and we have introduced the concept into a mathematical modeling language. And this is new. Yeah.
And this is generally closed source work. Is that correct? You don't publish
we never publish. Yeah, we never publish. The APIs are public. So all this language is available publicly. So you can see it. Now all the implementation and all the way we manage that internally, it's fully closed source. So first, because it was a question at the very beginning, do we go open source or do we so open source, I was not for, because I think that you cannot get the revenue to make a team of 50 or 100 living well, because if you want to have the best, you need to pay them. And today in optimization, it's very difficult to have the community effect, to have an open source projects, which is but run over the long term. It's because it's a small, it's optimization today, still small community, very expert, no community effect, and no scalability. But anyway, so yes, the key point is that we didn't publish paper because we are in the commercial race, but also it's not interesting for researchers. It's something I think we should. We tried to publish a few things at the very beginning. It was 2010. We published a paper. It's a very early thing. And we saw that it was not so interesting for people. It was very difficult to publish anything because it's like, it's like engineering. What is really new? And this thing is already. So, yeah, it was not very interesting. So we say, okay, if you don't find it interesting, we will implement it. We will make it work and we will sell it. And we will see. And yeah, apparently it was a good idea because here's the results we have. And again, I encourage you to check the benchmarks we have on Baker routing. So very different routing problems, capacitated, very large scale, time window, pickup and delivery, price collecting, split deliveries, whatever, driver breaks. So Hexaly is very, very robust. But more than routing, scheduling, the same, scheduling in discrete manufacturing, scheduling in process industry, project scheduling, but packing, clustering, matching, assignment, all these problems. We have a lot of benchmarks. If you want to check the benchmarks, hexaly.com/benchmarks. We have a lot of benchmarks, very factual. You can check that. And it shows where Hexaly makes a huge difference.
But I have a question from Ricardo. It's a more technical one. He's asking if he uses his own distance function, will Hexaly take advantage of it if the function is differentiable? Or will it resort to black box methods?
If you use you put your function in it, it's a black box function. Now we operate on. So we get points and we try to leverage as much as possible to see if there is a continuity, convexity, all this kind of stuff, and if it is differentiable, etc. So we try to find if there are some properties hidden behind the function, but of course it's a black box function. So now, if the function can be modeled analytically, yeah, we will have a closed form, and it would be easier for the solver, faster, etc.
Thank you so much for this talk, Fred.
Thank you.
We will be posting it online, and thank you everybody for listening in. I thought this was very interesting, and it's great to see someone trying to do it in a new way, shall we say?
Yeah.
Very good.
Thank you so much, all of you, for attending the meeting. Thank you, Torkel, for the organization, for the invitation, of course. Sander as well, all the team in the Euro Practitioner webinar. Yeah, thank you so much. And yes, I think if you want to have an idea of what is inside Hexaly, the presentation by Willemien, decision diagrams, is a good one, because we are really have inspired from the latest research in this domain. So coming from Willemien and Carnegie Mellon. Yeah, thank you.